Hello? Does this work or not? Yes. All right. It's my pleasure to introduce Ricardo Mendes from University of Oklahoma. He's going to talk about manifold submetries and their invariant theory.
Hello, can you hear me? Yeah. Okay. Yeah, thanks a lot for the introduction, Carsten. Thanks to the organizers for the opportunity to give a talk here. It's very nice, and thank you all in the audience for taking the time to listen to this. I hope I can be entertaining to some degree here for the next 50 minutes or so. So the title of my talk is Manifold Submetries and their Invariant Theory, and so this is some project that I've been working on for the last maybe 3 years or something like that, or a bit more maybe. There are some 3 papers. The last one is in preparation, so the last part of the talk is going to be a bit of like a work in progress kind of thing. All right. So yeah, let me start with what manifold submetries are, and let me start with like actually what a submetry is. All right. I'm sure many of you already know that, but maybe let's just go through it for those that don't know what that is. So yeah, so let's start with what's a submetry. So it's a metric space kind of thing. So let's suppose you have 2 metric spaces. Okay. Then you have a map between them. Okay, this map sigma is called a submetry when it takes closed balls in X to closed balls of the same radius in Y. Okay, so this is called a submetry. If so, if you take sigma of a closed ball in X, right, of a radius R, that is equal to the closed ball of the same radius R around sigma of P, right? So the picture that you could have here right is something like the usual projection from R2 to R, right? Then like you have a closed ball here, and you project it onto the x-axis, you get a closed ball here as well, right? Of the same radius. Okay, so that's what you should be thinking of. So this definition, I think, goes back to Berestovsky in like the 80s. I feel like that's when it was first defined this way. So some fact that we're gonna use later on is that this preserves lower curvature bounds. So if you have an Alexandrov space, if X is an Alexandrov space of curvature bigger than or equal to K, then Y is also, all right? So you have it improves curvature in some sense, right? So that's what a submetry is, and that's a purely metric definition. And then what is a manifold submetry from the title there? Okay, so what's a manifold submetry? Okay, so this is a submetry where the top space X is a Riemannian manifold. And you ask that the fibers of the submetry sigma are embedded smooth submanifolds of X. Okay, so manifold submetry is when the total space X is a Riemannian manifold. Let's call it M. And the fibers are embedded submanifolds. Let's say smooth submanifolds. And they can have, they may be disconnected. Okay, so I'm including here the possibility that some of these are actually disconnected. But then we asked that the different components of each fiber have the same dimension, right? So the dimension. And these submanifolds, they may have varying dimensions, right? If you vary the point x, right? This could have varying dimensions. I think this was defined for the first time, as far as I know, in paper by Grove and Chen from 2015 or 16 or so. I'm not sure if it was defined in these words before. I think not. Right? But submetries from a manifold without the explicit requirement that the fibers are submanifolds have been studied before by other people. Like I think Berestovsky and also Ricardo and Alexander Lichak. His thesis was about such things as well. Okay. All right. So what are some examples here of manifold submetries? So Riemannian submersion. Is one typical example of this. And another typical example is the quotient map, the orbit space map, when you have a Riemannian manifold and an action by a compact group by isometries. So the map onto the orbit space where G is, let's say, a compact group, and it acts on M by isometries. Okay, so quotients like that is also another one. And another class of examples is a little bit more generally than this, the quotient of M to the leaf space of a singular Riemannian foliation as well. So M going to M mod F, let's say the leaf space. Where F is a singular Riemannian foliation. Right, so this was talked about, so Diego talked about this in his talk, what are singular Riemannian foliations. But yeah, they're singular foliations where, so the singular foliations in the sense that they're generated by smooth vector fields, right? And where, like, if you have a horizontal, a geodesic that is normal to one leaf, it stays normal to every other leaf that it meets. That's the definition of singular Riemannian foliation. So that's, and okay, so maybe I should say here, with closed leaves. Okay. In general, singular Riemannian foliations are not required to have closed leaves, but to be an example of this, you need that. So I want to note one thing here is that if you take a submetry, in general, a submetry, and you have, so if you have a submetry and you look at the fibers of the submetry, they are pairwise equidistant. And in fact, a submetry is the same thing as a decomposition of a space into equidistant subsets. All right, so you can go back and forth between the like foliation point of view and the map, right, from one metric space to another point of view. Yeah.
Any simple looking example of a metric submetry where the starting space is a manifold, but which is not a manifold submetry? Because this equidistant things seems like, of course, there's a bit of regularity and wonder whether, you know.
Yeah, sure, of course. Yeah, you can take, for example, like let's say a convex subset in Rn. I think this should be true. Let's maybe make it simpler, like just like an interval in Rn or something like that. And you look at the distance sets to it. That forms a submetry. But like you have a boundary, right? Like the other leaves are smooth.
There is one leaf with
yeah, and the other leaves are like only C1 as well. Right? Yeah, like yeah, like yeah. like this, right?
That's completely abstract.
Yes, but in fact, it cannot be worse than that.
Okay.
Yeah. So this is result of Alexander Lichak in his thesis, right? That for in general, if you have a submetry in that sense from a manifold, then this is more or less the worst that can happen. On an open-dense set, it's a Riemannian submersion C1, and the singular ones, like, you can have stuff like this. Okay. In view of that result, I guess manifold submetries doesn't sound like it's much more restrictive.
Yeah, I was just trying to think which sort of singularities could occur and the boundary.
Yes. Yes. Okay. So right. So what I wanted to note here is that there's a one-to-one correspondence between submetries from a space to another space, and the compositions of Y into equidistant subsets. Pairwise, let's say, of X. Yeah, right. Into pairwise equidistant. Yeah. Subsets. Okay. So what's when are two subsets equidistant? Right. When like here's one of them, here's the other one. When like the distance from one point here to the other set doesn't depend on which point you chose on the first set. Okay. All right. So now I want to restrict attention here. So we're talking about manifolds so far. So let's take this manifold here and put like Euclidean space here. All right. So let me talk about those. Okay, so let's look at the case from now on. The total space is actually some Euclidean space. Okay. And I want to ask another thing about this. I want just the origin by itself to be a fiber. So this is sometimes called infinitesimal. Submetry or manifold submetry. Let's talk about manifold submetries only. Right, because it appears as the infinitesimal picture when you have a general manifold submetry. If you take a point on a leaf and take the normal space, in that normal space you have something like this. So the infinitesimal picture around the point looks something like this. So that's why it's called infinitesimal. So that's the case that I want to look at. And if you have a situation like this, in particular, you get that since the origin, I'm asking that the origin is a fiber, the unit sphere is foliated, right? It's like it's given by fibers, right? It's a union of fibers as well. So you get, and it's also a manifold submetry. So you get a manifold submetry on the sphere. And the point is that these two things are equivalent, actually, right? So you restrict to the sphere in this case. Okay, this is also a manifold symmetry, right? And you can recover the original one from this. So infinitesimal manifold symmetries are the same thing as manifold symmetries of a sphere. All right. So this is essentially Molyneux's homothetic transformation lemma. Is what's behind this. Okay. All right, so as I mentioned here, so what are some examples, right? In general, group actions are examples. Here, I want 0 to be a fiber, so a representation, right? Any representation of a compact group will give you an example of such an object, right? So if you have a representation, orthogonal representation. But there are actually many examples that do not come from group action like this. Like isoparametric submanifolds would be, all of isoparametric submanifolds are an example here too. So there are many inhomogeneous examples, right? So the example where the target here from the sphere is one-dimensional is essentially the same thing as being isoparametric. So this is an interval. This is essentially the same thing as, more or less here, as a parametric. Foliation. Right. So this is a very classical thing, right? Going back to Cartan, I think it was mentioned in some previous talks as well, as a parametric foliations. And there are many that are inhomogeneous. There are many that do not come from this. Okay, so this class that I want to consider here includes all of these as examples. Okay. All right. Do you have any questions so far about some of the basic definitions? Okay. Right. So the next thing I want to mention is that, in fact, this is a very this is an algebraic object. Okay. So far, like the definition is completely geometric, right? It's just in terms of metric spaces and something being submanifolds. Okay. But in fact, these are algebraic objects, right? So, which maybe is not so surprising, right? If you look at these examples, at least, right? These are very algebraic things here. And so this is called the algebraicity theorem. So let me talk about that now, right? Okay. So we're in the same situation as there. I have a infinitesimal manifold submetry. Okay. Infinitesimal manifold submetry. And then let's denote by Rv like this, the set of all, the algebra of all polynomial functions on V. Okay, so these are all the polynomial functions. This is a vector space, this makes sense. And let's consider the subalgebra, which we're gonna call B of sigma, of all the polynomials that are basic, in the sense that they are constant on the leaves, that is constant on the fibers of this map here. Okay, so there's a subalgebra of that. This is all the polynomials that are constant on the fibers. Okay, so far I'm just giving a definition, right? But here you already see where the invariant theory in the title comes from. In the case of orthogonal representation, this is the algebra of invariants, right? That's what people study in invariant theory. This algebra here, right? So as an example, right? If sigma is given as a map for a representation, right? Then this is the algebra. Is the algebra of invariants. Right, this has a rich history, of course, right? It goes back to, there was a lot of activity in the 19th century, with this, and it's still pretty active, right? And yeah. And the theorem, which I think is quite striking, and which is essentially, well, in the case of singular manipulation, is a Lichak-Rodetsky theorem. Okay. And we have extended it, me and Marco, in the manifold submetry case, but the proof is more or less the same. Okay, so we just kind of yeah, this is a small jump from here to here. It says that in fact this algebra here, okay, of basic polynomials, it completely determines sigma. Okay, it actually separates fibers of sigma, and moreover, it's a finitely generated algebra. Okay, so it says that this is a finitely generated algebra, so like pretty nice kind of algebra. And it separates fibers. Okay, in the sense that if you have two distinct fibers of this map sigma, you can find a polynomial that is basic, constant on, and has different values on the two different fibers. Okay, so in particular, you completely reconstruct sigma from this algebra. Okay, and it's a complete. That the fibers where I have to assume that they're infinity. Yes. I think it's enough C2, and then you. C2, okay, yeah. C2, but yeah, you want to rule out this. Oh yes, right. Absolutely. Yes. Yeah. Yeah. Here, I guess I just wrote smooth, but for there, yeah, that you need C2. Yeah. But you're right. You don't need C infinity. C2 is enough. Yeah. But then you get algebraic, right? These are algebraic varieties, the fibers. Yeah. So this theorem, right? I think it's very striking in this case. In these two examples that I wrote over there, orthogonal representations, this reduces to Hilbert's theorem. This is a classic theorem in invariant theory from like late 19th century, right? And in the case of isoparametric foliations, this actually was done by Münzner. These Cartan-Münzner polynomials will show up. This algebra is going to be generated by the Cartan-Münzner polynomial of the isoparametric foliation. Okay, so yeah, in those two cases, this was known before, right? And they're like this classic theorems. All right.
I'm confused about who is V and who is X.
In the theorem here? Yes. Yeah, so V is a vector space, is a Euclidean space, right? Any Euclidean space. Okay. And then sigma is a manifold submetry from V to some metric space X. That's the point. Yes. But this is not. Okay. Yeah. Infinitesimal in the sense that 0 is a fiber. Yeah, in the sense that 0 is a fiber. I'm also requiring that, yes. Okay. Yeah. Okay. Thank you. Oh, okay. Yeah, I wrote, yeah. Yeah, infinitesimal, yes. Yeah, no, thanks. This is, maybe it's a bit confusing because I didn't write it here, yes. All right. Right, and so as I kind of mentioned in words, maybe I'll just write it out here. That means in particular that the map sigma is completely determined by this algebra as a corollary of that. Right, so as a corollary, we get that the map sigma is determined by this algebra of basic polynomials, right? In the sense that its fibers are determined right? So 2 points in the vector space are in the same fiber if and only if the values of all polynomials in here are the same on both of them, right? They can't be distinguished by these polynomials here. Okay, so this gives you an equivalence relation, and the equivalence classes are the fibers of the map sigma. And as I mentioned before, the fibers and the map itself determine each other, all right? And in particular, we get that the fibers are algebraic varieties. So you start with smooth or C2 even, and you get that in fact that they're smooth algebraic varieties, right? Okay. Okay, so yeah, so this theory in particular tells you that, right, or this corollary, I guess, that there's a one-to-one correspondence, right, between manifold submetries, infinitesimal manifold submetries like this, and a certain class of subalgebras of the polynomial algebra, right? And so natural question is like, what is the image of that, right? What algebras are the algebra of basic polynomials for some sigma, okay? And this is known in the group action case as the inverse invariant theory problem, all right? And in that case, for group actions, as far as I know, this is solved in the case of finite fields, over finite fields, but not in other cases. And we don't have a good solution for it either in the group action case, but if you generalize to infinitesimal manifold submetries, then there is a nice solution. So that's in some sense what I think makes it natural from the point of view of invariant theory to consider this, right? So this is, yeah, inverse invariant theory problem. And so this is theorem. So this is in 2 papers, really. And it says that given an algebra, a subalgebra like this, then it is the algebra of basic polynomials of some manifold submetry, if and only if it's what we call a Laplacian algebra, which is an algebra that is invariant in the Laplace operator and contains r squared, the distance squared to the origin. So this subalgebra, right? Then over here. Right, then A is equal to the algebra of basic polynomials for some infinitesimal manifold submetry sigma, if and only if A is Laplacian. That is 2 conditions. It's preserved by the Laplace operator, and r squared, right, that's the sum of the coordinates squared, is an element. It's contained in A. Okay. Yeah, so note here that there's some duality between these 2 things, right? The Laplace operator is the dual of r squared, right? This is the sum of del xi squared. This is the sum of xi squares, right? So this is the right. So yeah, so I've been trying to convince invariant theorists that you know, it's more natural to do invariant theory over these objects than over group actions, just because like you have such a like natural answer to the inverse invariant.
We lost the audio for the Zoom.
We get now. Thank you. You like it?
Yeah, but like globally defined can you expand it? No, globally defined.
It's defined. Yeah, it's defined on an Euclidean space. It's infinitesimal in the sense that like if you have a general one and you look at a point and you zoom in, you see this.
But like above the look at is it coming from some compact manifold?
Oh, from a yeah, sure. You can take just like a what's it called, like on a sphere, right? Like a suspension, I guess. Yeah, yeah. You can make it a suspension if you want. So it looks like the Euclidean space, right? But then it just does it make sense? Yeah, the answer is yes on a sphere. You can do it. Yeah. Yeah, even if you want compact. Yeah. Okay. Right. So yeah. So what this tells you, right, is that there is this kind of one-to-one correspondence between some geometric object, this manifold submetries, and some algebraic object, this algebra satisfying these two algebraic properties here, right? So a natural question that we have been working on and different aspects of it is like, so you have a dictionary, right? What kind of like, given some geometric property of the foliation, what kind of algebraic property corresponds to it, right? On the other side of this dictionary. And we've done some of those, like what is, like when are the fibers of this map, when are they finite? When are they connected? And there are algebraic answers to that in terms of the algebra that defines them, right? One of them is that it's integrally closed somewhere. The other one is that the transcendence degree of the field of fractions is as large as possible. Stuff like that, right? But this is like a completely general question. You can hopefully work for this on this kind of questions for years to come, right? but yeah, this is just a completely general question here, right? So you have, yeah, geometry on one side, and then like algebra on the other side, right? And like, yeah, here's the manifold submetry, right? And here's its algebra of basic polynomials, which are just all the Laplacian algebras. And then any properties here, what does it correspond to on the other side, right? Some geometric property here, let's say like, I don't know, finite fibers, right? And here's the same thing as the transcendence degree of the field of fractions of the algebra is equal to the dimension of V. This is an example, but I want to concentrate on a more recent project, which also kind of goes in this direction, which is, let's look at the geometry of the base space, okay? The base space X of the manifold submetry, and more precisely on the volume of that, okay? So what I'm going to talk about now is a certain type of Weyl law, which gives you the volume of X, or rather the one over the sphere, right? The sphere, the compact one, right? So, yes, but here anyway, this is like this is a program, I guess, that can go on for a long time. But it's another example of this. For example, what kind of other geometric question can you ask here, besides like the fibers being this or that, is the base, right? What's the geometry of the base? Well, it's an Alexandrov space. This is always true. Okay, with curvature bigger than or equal to 0. It's also the cone over the image of the sphere, right? So you can do it on the sphere. All right, so Sx here is just sigma of the sphere, of the unit sphere. So it's a cone like that. And but it's actually much nicer than that, right? It's like it has a regular part where it's a Riemannian manifold. It's a stratified Riemannian space. This thing, so things like volume make the usual sense, right? You can just take the volume of the regular part in the Riemannian sense. You can define that way if you want. So let's talk a bit about the volume of that. And right, so what's the volume, right, of this spherical one, right? So this can be computed in terms of the algebra in the following way. So let's now look on the other side, the algebra of basic polynomials. So this is a graded algebra. Okay, so it's you know, there's a degree 0 part, a degree 1 part, etc. Right? Homogeneous polynomials, right, of degree 0, 1, etc. And from this, whenever you have graded algebra, what you can do is consider like a counting function, right? So the Hilbert series of this, right? So the Hilbert series, remember, it's a counting function that counts the dimension of each graded part. So it's a sum, it's a formal power series. And you look at the dimension times t to the power I, right? So it's a formal power series that encodes all those dimensions. And it's a general fact, like because it's a graded, it's a finite generated graded algebra and so on, that is actually a rational function. This is a pretty general fact with z coefficients, with integer coefficients. Okay. As a function of t, it's a rational function, right? It has a pole, etc., but it's okay. And it has a pole at some other point, right? So the theorem, which is, so this is now I'm getting into this work in progress that I have with Marco Hadesky and Sam Lin, gives you a way to compute that volume in terms of this series, okay, as an explicit formula. Right, maybe I should say in preparation, so theorem. Okay, let's see. Okay, LM, okay, Lin first. All right, so this is a work in progress here. Let's say in preparation. It's not out yet. And it says that if you look at this Hilbert series here, and you change variable, okay, this is a formal power series. Let's change variable to like 1 minus t and write a Laurent series. There's some certain coefficient here, and then powers of 1 minus t. The first one is actually a power dimension of the quotient, dimension of x. And then, there's the rest of it. So if you take this Laurent series here, then this coefficient here encodes the volume. Okay, so the theorem is that the constant C, this first coefficient here, is a certain universal explicit coefficient here. And rational number here, times the volume of Sx divided by the volume of the sphere of the same dimension, right? In particular, it's this is a rational number here, because this is a rational function with integer coefficients. Okay. So yeah, so you want to compute this volume. What do? You take you take this power series, change variables, look at the first coefficient. It's there. Okay. And in particular, there's a corollary here, right? Which is that this is a rational function, is a rational number, right? Which is not obvious a priori, at least not to me. But yeah, if you take the volume of Sx and divide by the volume of the dimension of the sphere of the same dimension, this is a rational number. Okay, so this is, I think it's useful to compare this to the finite group case. If you have a finite group acting on a sphere, right, what's the volume of the quotient? Is the volume of the whole sphere divided by the order of the group. So that's this number here is 1 over the order of the group in the finite group case. Okay, so here I'm saying even when you don't have either an infinite group or it's just a manifold submetry, this is still a rational number. Okay. All right. Do you have any questions here so far?
Can you say something about the poles of your function? They have any meaning, or do you know what?
Yeah, I think t equals 1 is the only pole.
It has the only pole. Okay.
I think so. Yes, I think so. Yeah, if you have
really clear from what you said.
yeah, I think it is. Yeah, if you have generate, like this is a finitely generated algebra. So you can use Noether's what's it called? Noether's theorem, and you get like a system of parameters, and you can find some nice set of generators for this, and then you can kind of write it as a polynomial over some like 1 minus t to powers like that, and these are going to be like the degrees of the generators. So if you find a set of generators, you can more or less just write this in terms of the degrees of the generators.
I was wondering, I suppose this is true already in the case of group absence? The volume of the orbital base?
I've never seen it. It follows from known results in a more or less straightforward way, but I have never seen this stated. Yeah, this fact. Yeah. Okay, so let me tell you like more or less where this comes from, and this comes from spectral geometry. Okay, so spectrum of the Laplacian and stuff like that, and I've heard someone complain outside that there was not enough PDEs in this conference. I'm not going to name names, but you know who you are. But oh, yeah. You've given yourself in. Okay. So yeah, let me finish here with a little bit of that. Okay. So where is this result coming from? Right, it's coming from spectral geometry. So here, let's take a step back. In fact, this is more general. So let's go to a manifold submetry. Okay, from a general manifold. I'm not in an infinitesimal case anymore. All right, compact. Okay, and actually we also need one more condition, which is that the fibers, they have the mean curvature vector of the fibers is basic. it kind of doesn't change when you move along the fiber. That's a technical condition. Maybe I won't write it here. And then you can look at the basic spectrum. Okay, so if you look at for each number lambda, the basic spectrum. Okay, so you can look at all the eigenfunctions, right? The basic functions f, which are eigenfunctions of the Laplace operator with eigenvalue lambda. Okay, so this will be the eigenspace, the basic eigenspace. And then the theorem that we have is a kind of Weyl law. It's the same group of people, same paper that's still in preparation. It says that it's a Weyl law, right? So it says that the rate of growth of the dimensions of this thing here, the volume shows up in there. Okay, there's a specific rate of growth, and a coefficient is exactly the volume of the quotient. So if you look at the sum for of the dimensions of these spaces. Okay. As you make this mu parameter go to infinity, okay, the counting function of how many eigenfunctions you have, this has the following asymptotic behavior. The volume of the quotient shows up, times a certain universal constant that doesn't really matter too much, times mu to the power m over 2. So m here is my notation for the dimension of the quotient. Okay, so you have a particular growth here, polynomial growth. Moreover, the coefficient in front of it tells you the volume, right? So this is the Weyl law. Okay, if the foliation is just by points, right? So everything is basic. This is the classic Weyl law. Okay, and in the case of a group action, this was known before. And this is the theorem of Bruning, Heinze, and Donnelly from like the 70s, where they have exactly this result for group actions. So what we did is extend from group actions to manifold submetries, right? So this is yeah. So that's that, and how do you get what I wrote over there? That theorem is a corollary of this one, okay? And the way you get it is by noticing that you can write down the eigenvalues, right, of the Laplacian in terms of this Hilbert series. Okay, one thing determines the other, actually, right? So as an example here of this theorem, if you look at the case where the manifold M is just a sphere, okay, then and you can look at yeah, what are the eigenvalues of the Laplacian, right? Yeah, you can compute them in terms of the harmonic basic polynomials, right? Essentially, right, of degree d, where d times d plus n minus 2 is equal to lambda, right? So what I'm alluding to here is the theory of spherical harmonics, right? So what is a eigenfunction of the Laplacian on the sphere? It's the restriction to the sphere of a polynomial which is a homogeneous polynomial and which is harmonic, right? Right, and then what are all the polynomials, right? They are like, you know, harmonic, and then if it's not harmonic, you take a part that's not harmonic, you divide by r squared. There's a harmonic part there, etc. Right? You can decompose any homogeneous polynomial as a sum of like powers of r squared times harmonic polynomials, right? And using that, you can count this thing. So the basic spectrum contains the same information in this case as it actually has this it's counted by this function here. Okay, in terms of counting functions, you can just take that Hilbert series, multiply with the 1 minus t squared, right? This takes care of this like counting and stuff. And this essentially, this function here counts the basic spectrum. Okay, so this contains the same information. So when you see the growth of this from the Weyl law, it tells you the growth of the coefficients of this, and you can tell, and it's not hard to see just from like formal power series that the growth of coefficients of a power series like this is encoded in the first coefficient of the Laurent series at 1. Okay. All right. Yeah, that's all I had. So thank you for your attention.
Thanks very much for a beautiful talk. Any questions or comments?
So thanks for your overview. I was wondering, perhaps you already mentioned, but in case I ask you, to repeat once again, the if and only if theorem, I mean, the one that was on that blackboard that you erased a few minutes ago, concerning, which algebras actually, are coming from this kind of construction. So what is the I mean, where this conditional Laplacian and R square come from? First question, and related,